Hello everyone. So once again we are back with another video on real numbers. And this time we are going to discuss the irrational numbers of part of it. In the previous videos we discussed rational numbers and now we are going to discuss irrational numbers. So a number x, y, z or s here is called irrational if it cannot be written in the form of p by q. So if there is any number which I cannot write in the form of p by q, that is irrational. So if I can't write it like this, so the number I suppose is x here. So if I can't do this, that number will be irrational. Okay, great. So here p and q. So p and q are integers and q is not equals to 0. So q cannot be equals to 0. But the question is that you will be often asked in the examination is, how do you prove it? Okay, now let's see. One way that we can solve it is by proof by contradiction. So here the question is, let us prove root 2 is irrational. Now this is a question which has actually been asked in the board examination a couple of times. So this is a very important question from the exam point of view. Now here the proof states that first we have to assume to the contrary. So now we have to prove root 2 is irrational, but we are going to assume that root 2 is rational. So we can find integers r and s such that root 2 is equals to r and s. Now suppose r and s have a common factor other than 1. Now then we divide by that common factor to get root 2 is equals to a and b. So we found a common factor between r and s other than 1 and then we divided it by that number to get root 2 is equals to a and b. Now because we did that, now we know that a and b are coprime. So if we solve the equation, that would be that root 2 will be equals to a, as you can see here, because b goes here and then it becomes b root 2 is equals to a. Now if we square this on both sides and we rearrange it a bit, we get 2b square. So because of under root and squaring it up, we got 2 and b square is equals to a square. Now this means that 2 divides a square. And if you remember the theorem 1.3 in the NCERT, you would understand that if 2 divides a square, it will also divide a. Now we can write a is equals to 2c. Why? Because we know that 2 divides a, therefore a must be a multiple of 2. Therefore 2c is equals to a. Now let's move on to it. So now we are going to substitute for a. Now we get 2b square equals to 4c square. Okay, because what we did here, once again let's see that we had a is equals to 2c and now what we are doing is substituting for a. Where are we substituting exactly? Where we are substituting? We are substituting it here. Okay, now we already know 2b square is equals to a square and a is equals to 2c. Therefore 2b square is equals to 4c square. Great. Now this means that b square is equals to 2c square. This would also mean that 2 divides b square. And we know that if 2 divides b square, 2 divides b also, once again using the theorem 1.3 in the NCERT. Therefore a and b have at least 2 as a common factor. This means a and b have at least 2 as its common factor. But if it is true, this contradicts the fact that a and b have no common factors, because at first we assumed that because we have divided it by the common factor r and s, a and b are coprime. But now we came to know that a and b actually have a common factor, which is at least 2. But this contradicts our statement. Therefore, this contradiction has arisen because our incorrect assumption. And what was the assumption at the very start? That root 2 is rational. And because our assumption is incorrect, it contradicts. Therefore, we can conclude that root 2 is irrational. Okay, great. I understand that it's a kind of a long drawn process, but it's very important from the examination point of view. And I would highly recommend you to learn it by heart and be able to do a lot more questions like root 2, root 3, root 5 and so on. Great. Now let's move on to the next question. So here it states that prove 3 plus 2 root 5 is irrational. Okay. So now again we are going to try to do it by contradiction. So proof by contradiction. Okay. Now here, let again 3 plus 2 root 5 be rational. Okay. Now if that is the case, this means that we can, so if that is the case, this means we can write 3 plus 2 root 5 in the form of P by Q. Right. Now we already know if I do it this way, this means that now root 5 would be equals to 1 by 2 upon P by Q minus 3. I did not do anything, I just transferred the numbers from here to there for us to understand it properly. So I took 2 root 5, so this step came when at first before I did this. Okay, I did this at 2 plus root 5 would equals to P by Q minus 3, and then root 5 would equals to 1 by 2 P by Q minus 3. This is how we got this step, then this step, and then this step. Now we know that 1 by 2 upon, and in the bracket P by Q minus 3 would actually be a rational number. And now we can easily prove by the same method we prove that root 2 is an irrational number. We will prove that root 5 is also an irrational number. And once we do that, what we can say that if root 5 is irrational and root 2 is rational, therefore root 5 cannot be equals to 1 by 2 P by Q minus 3. Therefore 3 plus 2 root 5 must be irrational. Got it? Great. Now let's move on to the next question. But first you can see the solution here, as it is clearly mentioned that how to go about it. And once again, all we did was rearranging in the very start, and because we got to know that 1 by 2x upon in the bracket x by y minus 3 will give us a rational number, while we know that root 5 is not a rational number, therefore it is contradicted here, and we concluded that 3 plus 2 root 5 is irrational. Great. Now let's talk about rational numbers and their decimal expansions. Okay, so what are rational numbers? So rational numbers have this tendency of being terminating or non-terminating and repeating. Okay, this means that any number which can be expressed in the form of P by Q is either terminating or a non-terminating repeating number will be classified as a rational number. Let's understand it very easily. So if the number is in the form of P by Q, then its Q must be equals to some factors of 2 to the power m and 5 to the power n. Okay, so it should be a multiple into 2 into 5 with any number of power. While if it is non-terminating and repeating, in that case, in the P by Q form, Q will not be equals to 2 to the power m and 5 to the power n. And here, m and n, both of these are non-negative integers. And why do I say non-negative and not just positive? Why? Because 0 can also be one of the value. So here the power can be 2 to the power 0 and 5 to the power 1. That is also possible. Okay, great. Now let's have a look at it. Now rational numbers have either a terminating decimal expansion or a non-terminating repeating decimal expansion. Okay, that's what we discussed in the previous slide. So in the first example, you can see with 3 by 8, I can write 3 upon 2 by 3. And 3 upon 2 to the power 3. And I can also multiply it by 5 to the power 3. And this won't change because we are multiplying it on the both sides, and we can see 2 and 5 both have the power 3. So here our m is 3 and n is also 3. Therefore, this becomes 10 to the power 3 if we multiply both of them. and we get a number which is a terminating decimal expansion. So this is a terminating decimal expansion. Once again, if I look here for example number 2, once again in the Q part we have 125. 125 could be written as 5 to the power 3, and I can multiply 2 to the power 3 in numerator and denominator, which would once again give us 2 to the power m into 5 to the power n, which would once again make our m3 and n3, will give us the number at the end 104 divided by 10 to the power 3 will give us at the end a final number with a terminating decimal expansion which is 0.104. So once again this is a terminating one. For 7 to the power 80, we once again have the same formulas that we can multiply 2 to the power 4 into 5 to get 80. Then I could multiply 7 into 5 to the power 3 and also multiply 5 to the power 3 in the denominator, which would make m and n both equal in the denominator, which once again would give us a terminating decimal expansion, and so is the case with our example number 4. It is also in terminating decimal expansion. Now let's move on to solving questions. So here the following real numbers have decimal expansions as given below. In each case decide whether they are rational or not, and if they are rational in the form of p by q, what can you say about their prime factors of q? Okay. So first of all we can see in example number 1, this is a terminating decimal expansion, and because it is a terminating decimal expansion, this is a rational number. So this is rational. And what can I say about the prime factors? Okay, so I can write 43.123456789 in the form of 43 1 2 3 4 5 6 7 8 9 and divided by 10 to the power 9 to get the same number of zeros, right? And we already know that I can write this as 2 to the power 9 and 5 to the power 9. What we can say about the prime factors of q? That they are 2 and 5 with the power of 9 on both. Great. Let's talk about question number 2 now. So here we can clearly see it's 1 2 0 1 2 0 0 1 2 0 0 0 1 2 0 0 0 0. This means it is a non-terminating, because we have 3 dots here. This means it's a non-terminating, but at the same time non-repeating, because it is not repeating any kind of pattern. Therefore this is an irrational number. This means that we cannot write it in the form of p by q. While here once again this is non-terminating because we have bar at the end, so it's non-terminating. But at the same time, because we have bar, so we know there is a pattern and it is being repeated over and over again. So therefore this is repeating, and because it is repeating, it is a rational number. And because it is, once again, what we can do, we can solve it exactly in the case of our option number 1, and we can find out about the prime factors of q. Great. Now with this, you have come to the end of this video, and I'm sure that all of you understood a lot about irrational numbers and how to solve these questions. At the same time, I would like to emphasize once again that solving the proof questions for if root 2 is rational or if root 3 plus root 2 5 is rational, all of them are very important from the examination point of view. So do give enough of time on these type of questions. With this, I will meet you in the next video where we will be solving a lot of questions for the real numbers together and see how much thorough we are with the concept. Thank you so much for joining in. Have a happy learning with EduRev.